Hello and welcome to this session on AOT or JIT, faster startup or faster code. My name is Simon Ritter and I'm the Deputy CTO of Azul. The idea behind this presentation is to look at specifically microservices from a performance perspective when we're dealing with Java-based microservices and think about some of the challenges that we have in terms of those performance characteristics. And as the title suggests, are we more interested in how quickly we can start up those services? Are we more interested in how fast those services will run once we've started them up? Or are we interested in both? And how can we achieve different aspects of those things? So the first thing that we need to look at is in terms of a Java-based microservices, what are the performance challenges that we're actually faced with looking at it in terms of the Java virtual machine? One of the great things about having the Java virtual machine is that we're running in a managed runtime environment. What that means is that we don't have to worry as developers about things like memory management. Allocation of space for objects is handled for us automatically. The garbage collector reclaims the space when we no longer require it and makes it available for new objects. All of that's very good, but it does come with a price in certain situations. One of those things is that we often see with the JVM that we can get increased latency for applications, as in how long it takes to respond to a particular transaction request. And that's often as a result of garbage collection. The reason behind that is that most garbage collection algorithms, the way they work is that in order to relocate objects within the heap so that you can eliminate fragmentation, they have to pause all of the application threads to be able to do that safely. The longer it takes to actually do all of the garbage collection work, the longer the pause is going to be associated with the JVM and the longer the application code is going to have to wait for that. There are some other reasons that we see pauses in JVM applications. JIT compilation is one of those. In fact, the implication of de-optimisations, which we'll come back and talk to a little bit more later on. These are all things that we need to consider. Then we have the situation about throughput. How many transactions can we process in a given time? How many transactions per second can we deal with? And our ability to do that is dependent on how the code is compiled to run for our application. And again, we'll come back and talk about this in a lot more detail as we progress through the session. But it's about looking at this idea of just-in-time compilation, the ability to optimize based on a very clear view of what the application is actually doing at this point in time, but also how the application has run up to the time when we're doing the compilation. And so the effectiveness of the just-in-time compiled code is going to give us a lot of input and a lot of effect on how much throughput we can get for the application. And then the third aspect of performance and our challenges that we need to think about is how quickly we can start up a Java virtual machine based service. How quickly do we need to load up classes? How long does it take to initialize classes? That type of thing. And then again, the whole aspect of just-in-time compilation, because we're going from interpreted bytecodes through to quickly compiled but low optimized code, then onto heavily optimized code. How long it takes to identify all the methods that we need to do that for is going to be how long it takes to get to our optimum level of performance. This is often called the warm-up time associated with the Java application. So these are our JVM performance challenges. Now, let's have a look at that specifically when we're thinking about performance and speed in terms of a microservice architecture. So what I've got here is an example of an application which uses microservices. This is great because it moves away from the older design pattern of a monolithic approach. What we're doing now is we're taking the whole application, we're dividing it up into a number of individual services, linking those together. Now, this has many benefits, especially when we're dealing with a cloud environment. By putting our individual services separated, we can put those into containers. It makes it simple from a deployment perspective. We can then use things like Kubernetes to orchestrate those services and move things together and have everything work in a nice environment. So having this idea of microservices-based architectures is very good from the design perspective, but there are other advantages as well. One of those big things is that what we might find is that one of those services becomes a bottleneck. Many other parts of our application rely on that. Let's say it's some kind of transaction processing, credit card transaction processing thing, and everything depends on that. In that situation, if we were doing a monolithic architecture, then we'd really be kind of stumped in terms of how to improve the performance of the application overall. Realistically, the only thing we could do at that point would be to provide more resources, more CPUs, more memory, and so on for the whole application. But that's very inefficient. With a microservices architecture, we can look at that and say, that particular service is a bottleneck in terms of the performance. And what we then do is we say, okay, let's solve that by creating more instances of that service. If we're clever in terms of the design, we can separate out the state that we need into other parts of the system. So these services, we can spin up as many as we want, and then again through our Kubernetes system or whatever, we can then direct requests so we can load balance across those multiple instances. This is very good because clearly it solves one problem of not having to throw resources at the whole application, just at the one that we need to. But it's also good from being very dynamic. When a load increases and we do need more instances of those services, we spin them up, provide the required service for that, and then as load drops off, we can then shut down those services, and that avoids over provisioning. It avoids the whole issue of spending more on our cloud environment than we actually need to. So we can be very dynamic, very responsive to changes in load, and therefore be very efficient in terms of our use of the resources that we have. Now, one of the other things that we do need to consider in terms of our architecture for this microservice-based application is how many microservices we involve in this. The reason for that is if we think about our users, what's actually happening here is the user is interacting with our application. From their perspective, they don't actually care that there are a number of services involved. What they're interested in is using their web browser, connecting to whatever application it is that we're providing, doing something, making a transaction, waiting for a response to that. What they're saying is how quickly do they get a response to their particular transaction. Now, what that involves is clearly a number of different services within our architecture. So we have our transaction flowing through these individual services. From a performance perspective, what we've really got to consider here, and this is especially true when we talk about Java services, that the latency associated with the transaction from the user's perspective is going to be an aggregate of the latencies of each of those individual microservices. So we have to add those things up. If we're doing garbage collection in each of those services, then that latency associated with the collection adds up as we have more services. This clearly means that when we're designing our application, we need to think carefully about how fine-grained we should make our services. If we make them too fine-grained, then we lose in terms of the latency adding up and therefore delaying transactions for our users. If we make it too coarse-grained, then we lose on the side of being able to spin up new services and respond in a more dynamic way. So what we're looking for is somewhere sort of in the middle, where we've got not too coarse-grained that we can still take advantage of spinning up new services, but not too fine-grained that we're losing in terms of the overall performance. And that's one of those tricky things that we need when we're designing our application. Okay, so let's look at those things in terms of the specific things that we need to think about when we're developing a microservice and from a performance perspective. So this ability to spin up new instances and how long it takes to do that. And one of the things clearly we've got to think in a Java environment, how long does it actually take to provision a new cloud instance? If that's going to take a long time, then how long it takes for the Java application part, the Java service, to come online may not be significant compared to the time it takes to provision the new cloud instance. Obviously, we've got the warm-up time associated with a Java piece of code. how long it takes to compile those methods to get to that heavy optimized level. This is especially relevant when we talk about the sort of extreme side of microservices and serverless computing, or the AWS lambdas. Essentially what you're doing there is starting up a service, providing some kind of function that does something, and then stopping the service immediately. In that situation, it may not be the case that Java is the right platform to use for that, because it's very short-lived. You might not actually get any benefit in terms of the performance you would normally get with Java. For many services, because they're longer running, then that's where Java becomes the win in terms of performance. Second thing we need to think of is, once we've got that service started up, how much throughput do we get for that service? And this is especially important when we're thinking about transaction processing capability and how many instances of a particular service we need to do something. When we look at some bigger services, if we think about, Cassandra or Hadoop or something like that, where even though those are technically a microservice, they're doing one thing, doing it well, we would then break that up into a number of instances, have a cluster of nodes. The more throughput we can get through each of those nodes, the less nodes we'll actually need in our cluster to handle a given number of transactions per second. In a cloud environment, that's obviously cost. So if we can reduce the number of nodes, we're reducing our cost. More throughput means cheaper. And then lastly, again, the latency aspect, which can impact on the number of instances that you require, because if you're having to wait too long for a particular instance to respond, then you might start spinning up new instances to be able to respond to other requests. And in an extreme situation, if you've got a very long pause, maybe it's a big thing and garbage collection kicks in and it takes seconds to actually respond, the underlying control system, Kubernetes, for example, may decide that that service has actually gone offline and do a restart on it, or might start up other instances. So that's the sort of extreme end of things that we need to think about. Okay, now let's talk about AOT and JIT, which are two approaches to how we can provide native executable code for an application that's running part of our code. So we look at Java compilers, and specifically around ahead of time compilation. What we can do is we can take Java code and we can decide that we want to compile it into a set of native instructions straight away. Rather than compiling to bytecodes and then letting it run on top of the JVM, we say, let's compile it into a native application, just as we would with C or C++. Now, one of the things that immediately does is it loses the write once, run anywhere idea that we've always had within Java. So you can't simply take the same application and deploy it onto an instance of Linux running on Intel versus Windows running on ARM. You have to say, right, I'm going to be using this specific operating system, this specific hardware. But the other thing that can kick in here is even though you're compiling to a specific hardware platform, you still don't know exactly which hardware you're going to be running on when you start the application, or you may not do. What do I mean by that? Well, think about it. Okay, we're going to run on an Intel processor. So we know that we have to compile into the x86 instruction set or x64 instruction set. That's all good. The thing is that processors evolve over time, and Intel adds new features to that to make it easier to do certain things with certain instructions. Really good example of that is vector processing, single instruction, multiple data. Now, this has been around for a long time, nothing new. What we do there is we provide a wide register, 128 bits or more, and then we can load up multiple elements of an array, and then in a single machine instruction clock cycle, we can process all of them in parallel. So it's great for numerically intensive operations. But the thing is that depending on the age of your processor, you either have AVX, AVX2, or AVX512 instructions. More modern ones obviously have all of them. When you compile your code, do you guarantee that you have access to AVX512, so you know you've got to run it on a particular version of the processor? Or do you say, okay, I don't know exactly which processor I run on, so I will compile it to the lowest common denominator? So I'll use AVX instructions, but I won't use AVX 512. That's going to limit the amount of performance enhancement you can get from those things because you're not able to use the exact instructions that are available on the machine you're running. The other thing that's very significant with ahead of time compilation is that it is static compilation. So you're doing static analysis of the code paths that are being used. What you don't have is any idea of what's happening at runtime because you're compiling it before you run it. Now, Java as a language is very much statically typed. You can't change the type of variables as the application is running. But Java is dynamic from the point of view of class loading. That's one of the real benefits, and it gets used in a lot of frameworks. So when you run an application, code can be loaded at runtime that will replace certain classes and therefore will replace certain methods. This is significant because when you look at one of the most common optimizations that are used for compiling code, it's method inlining, avoiding the overhead of creating a stack frame, calling the method, and then popping the stack frame back off again. What you do is you simply take the instructions of that method, put it in line with the code, and avoid that overhead. Problem is that you can't be as aggressive with your method inlining if you use ahead of time compilation, because you can't necessarily guarantee that the method that you're going to inline at compile time is going to be the one that will be used at runtime. If someone does a dynamic class load, replaces a method, when you call that method, it's a different one, and so you can't necessarily inline everything that you would want to. So the opportunities for optimization are reduced. As I say, less aggressive method inlining. Also, you can't use speculative optimisations. I'm going to talk about that in a moment because that's a real big thing. And then you've got to think as well that when you actually run your application, it's a Java application, you statically compiled it, how do some of those things happen that the JVM would normally do for you? It does allocation of memory, it does garbage collection. Now, if you compile it in static code, how does garbage collection happen? Because you don't have a garbage collector in your code exactly. So you've got to include that into how things happen. Just-in-time compilation. This is the other way of doing things. Now, obviously here, what we're doing is we're compiling the code as it runs. What that means is that we can have a full, clear view of exactly what's happening at runtime. That means we know exactly what classes are loaded at any point in time. If we want to compile a method, then we know all of the classes and methods available. So when we do our method inlining, we know exactly which method to inline because it's there and we have visibility. That means we can be much more aggressive in terms of that and get better performance in that way. The other thing is, again, speculative optimizations, which I will explain in a moment. But the downside, if you like, is that that extra compilation that we're doing as the system is running is going to detract from the ability of the application to do its own work. We've got cores doing compilation in parallel with the application, so that's taking away resources that we could use to do the work of the application. So while it's doing its warm-up, especially, there could be a degradation in terms of throughput before we get to our steady optimized state. Speculative optimizations. I've mentioned this a couple of times. What does this really mean? What are these things? Well, this is an example. It's a slightly contrived example, but it's good to illustrate how things can actually work in terms of code as we use a JIT compiler. In this method that I've got here, it's called compute magnitude, and it takes a value as a parameter. Within the method, what we're doing is we're saying if the value is greater than 9, then we need to call another method called compute bias, passing value, and that will calculate the bias that we're going to use within our method. If the value is not greater than 9, then we just set the bias to be 1. And then we return math log base 10 of the bias plus 99. If we profile our application whilst it's running, we may find that during the whole time that we've been running our application, the value that's been passed into this method has never been greater than 9. Okay, what we can then do is we can speculatively optimize that code. And what that means is that we can say, let's assume that because the value hasn't been greater than 9 so far, in the future, that will also hold true. In that case, what we'll do is we'll eliminate a lot of the code that we would have had to call. We can see here that we can recompile that based on this. We say if the value is greater than 9, then we have to call uncommon trap. Now, I'll come back to that in a moment. Assuming that the value isn't greater than 9 and it continues to do that, we know that bias will always be 1. 1 plus 99 is 100. Math log base 10 of 100 is 2. So rather than actually calling that method and calculating that, we simply return 2. Much less code involved and much higher in terms of performance. Obviously, we still have to deal with the situation where we might get a value greater than 9, because otherwise we're not fulfilling the contract of the compiler. If the value does happen to be greater than 9 at some point in the future, then we call uncommon trap. What that does is it says, right, our speculation about the optimization was wrong, so we have to throw away the compiled code because that's now incorrect, and then we have to recompile it based on both of the branches in that if statement. So what we really want to do is avoid as much as possible those de-optimizations, but you can see how this would benefit in terms of performance. So speculative optimizations, what we found, Azul, in terms of looking at the benefits in terms of performance, over half the performance benefits we get from JIT compilation are down to speculative optimizations. So that's absolutely critical for the best possible performance. And again, as I said, in terms of the best results, what we want to do is minimize as far as possible, ideally eliminate any de-optimizations. We're not going to throw away code that we've already generated and then have to recompile it. Now let's look at how we can take different approaches to solving the startup speed problem. This is something in a microservices architecture where we need to think about what's the best possible approach. So one of the things that's become quite popular recently, a lot of people have been looking at this, is the Graal VM. Graal VM is a slightly different approach to how we take Java code and other language code and do something with it in terms of performance. So GraalVM's been around for quite a long time. It actually started as a research project at Sun Microsystems, and it wasn't really the Graal VM. It's actually a really bad name for this. It's a number of different projects that were started. The substrate VM, which is what the VM really is called, is substrate, the Graal compiler, and then the truffle framework. So these are the kind of three core things that make up Graal. So Graal, as you can see, is really designed around polyglot applications, not just about Java. It's about running scripting languages like Ruby, JavaScript. It's also running more traditionally compiled language, statically compiled languages like C and C++. So how does this work? Well, I won't talk too much about the non-Java languages because the presentation is really about what we do there. But as you can see, in terms of C and C++, what they do is they use a thing called Sulong, which is related to LLVM. And LLVM is a compiler project for generating statically compiled code. What that will do is generate an intermediate representation, which we can also do from scripting languages like Ruby and JavaScript. And then the truffle framework is what will be used to generate from that something we can then compile using the Graal compiler. On the Java side, we don't need truffle because we already have bytecodes. So what we would do is take those bytecodes and pass them into the Graal compiler. Graal compiler is written in Java itself. And what it will do is essentially compile bytecodes into native instructions. When we run that, we have two choices. We can either do it in the traditional way that we've seen before, where we can use the JVM. So the difference and the advantage, if you like, is that you're using a different compiler for the JIT. So you're still doing JIT compilation for Java if you want to, using Graal rather than the C2 JIT compiler, which is what you get in Hotspot. That uses the Java virtual machine compiler interface and then can sit on top of OpenJDK and run in exactly the same way that you would before, hopefully getting better performance. The alternative is that you can compile into a native executable. And to do that, as I said, in terms of being able to deliver the functionality that's required, like garbage collection, memory allocation, thread synchronization, all of that's handled by the substrate virtual machine. And that's essentially a virtual machine that gets compiled into your application so that when the application code runs in native instructions, when it needs to allocate space, the substrate VM will handle that. And the substrate VM will also have a thread running that says, right, if we don't have any use of that object anymore, reclaim the space and then make it available for other objects. So that's the sort of idea behind GraalVM. Now, from a performance point of view and for Java applications, as I said, you can run just a straight bytecode. You're replacing the C2 JIT compiler with Graal compiler and get hopefully better performance that way. For microservices, what people are often looking at is using a native image. So now we're doing ahead of time compilation and generating a native executable specific to a platform. If you ask Oracle, they will claim that that's actually 50 times faster in terms of startup, because you're not having to go through all the normal Java application type things. You're just going straight into native code running on that platform. So yes, you probably do get much faster startup. They also say that because you don't have all the overhead of all the sort of Java virtual machine side of things, you can get up to 5 times smaller in terms of the resource utilization, which for certain microservices could actually be a big advantage. As I said, we use a substrate VM to handle the managed runtime functionality, and it's something to consider from the point of view of performance, because in that case, what we need to think about is how memory management happens. You know, we have lots of different garbage collection algorithms that get used in hotspot. How does it actually happen in the substrate VM? The way it does is through a hybrid kind of effect, or a way of doing things. It's region-based allocation, static analysis, and so on. So all sorts of things to understand there. What can we do from Azul? So we've been looking at how to improve the performance of the JVM for a long time now. And what we have is a thing called Azul Prime. It used to be called Zing. We've recently rebranded it, so it's now called Azul Prime. And we have another set of technologies that's part of that, which is called ReadyNow. So the Azul Prime JVM is where we didn't start from scratch. We didn't say to ourselves, let's do a clean room implementation like IBM's J9. OpenJDK, lots of that code is really, really good. No point in us trying to rewrite it. But there are certain aspects of it that we think we can improve. What we've done is to change things like garbage collection. We took all the hotspot garbage collectors out, CMS, G1, Shenandoah, ZGC, and replaced them with one that we call C4. Truly pauseless collector, eliminates the problem of garbage collection latency. And I'm not really going to talk about that today because we're talking more about the AOT versus JIT side of things. What we've also done is, in the same way that Graal replaces the C2 JIT compiler with the Graal compiler, we've replaced C2 with one that we call Falcon. Falcon's based on LLVM, open source compiler project, already mentioned that, and we'll come back and talk a little bit more about that in a moment. And then we've got this idea of ReadyNow and compile stashing, which reduces the warm-up time associated with our application. Now, how ReadyNow works is that you say, okay, let's run our application and let it go through the normal warm-up process. So we run it in production. There's no problem with that. We don't need a test environment. Run it in production, have people interact with it, give it a totally characteristic load. So we're not trying to fake the load that we provide for it. We're just saying run the application in production with real users and real transactions, and get to a point where we're happy with the level of performance and the methods that we think need to be compiled are being compiled. At that point, we take a profile, and that profile consists of 4 pieces of information. All the classes that are currently loaded, all the classes that are currently initialized, doesn't necessarily mean it's the same set. All the profiling data that was collected during the interpreted mode and the C1 compiled JIT compilation code, because that's what's used to figure out how to optimize using C2 or Falcon or Graal. And most importantly, all the speculative optimizations that failed, where we made an assumption that was wrong, we had to throw away code and recompile. We can gather this data over a longer period of time. We could wait 2 minutes, we could wait 2 hours, we'd wait 2 weeks if we want before taking that profile. And by doing that, we can see which optimizations work and which optimizations don't. When we have this profile, when we start the application again, rather than going through the exact same process of profiling and compiling and all that sort of thing, what we do is immediately say, we've got all this information, So let's load all the classes that we know need to be loaded, that we can load. Let's initialize all the classes that we can from that list. And then let's take those methods that we know need to be compiled for our application, use the profiling data that we've already collected here, and know which speculative optimizations failed so we don't make those mistakes again, and compile the code before we start running the application. So before we get to main, we've compiled all the methods we need. And what that means is that you literally get about 98% of the performance that you would have had when you took that profile. So if you've run the application for 2 hours, you've got the same, almost identical level of performance as you would have had at that point. We don't get quite 100%. There are a few things that, because of the way the JVM is specified, that you can't necessarily do everything that we would want to do. And things like lambda expressions, because of the fact that they rely on invoked dynamic, they can be a little bit more challenging in terms of the way that we actually optimize based on that. So realistically, you need about 3 or 4 transactions just to get to that 100% level of performance once you've done a ReadyNow profile. Now, if we look at a simplified graph of how this looks, without ReadyNow, what we're going to see is a graph that gradually increases in terms of performance over time. This is where we're compiling all of our methods. So we start off in interpreted mode that's slow, compile methods through C1 and then Falcon, get to that steady optimized level of performance. It takes some time to do that. That's without ReadyNow. If we do it with ReadyNow, we get a much better graph in terms of the startup. So we're going straight away very, very high and get that optimum level of performance. There is just a little bit of a drawback though, because obviously what we've got is this kind of blank bit before the application starts doing any work. And this period of time is where we're doing the class loading, the class initialization, and the compilation. This may not be a problem for certain applications. If you're doing a trading application, then what's going to happen is you say, right, we need the application to run at 100% at 9 o'clock in the morning. So we'll just start it up at 5 to 9, 10 to 9, let the system do all of its work, and then at 9 o'clock it's ready to go. But for things like microservices, that might be more of an issue. So what can we do about that? Well, obviously we can do different profiles and we can look at how to improve things that way. And one of those things here, we can see that in terms of latency, if we take the original application, that's the sort of light blue line there, what we see is that the latency starts off very high because we're running in interpreted mode, and then we gradually compile, drops off. By using different profiles, we can greatly reduce that and provide better overall effects. But if we look in a little bit more detail at how things work inside our Prime JVM, what's happening is we're taking our bytecodes and we're converting them into the LLVM intermediate representation. That's what we pass to LLVM to compile and generate native instructions. To do that efficiently, LLVM actually needs to send some queries to the VM to understand information about profiling. So what things happened, how optimizations could be used, and so on. So it will send us a series of queries to the virtual machine, and it will get back responses that it needs to use to generate the code. Having got those responses, it then compiles, generates machine code, and returns that as a compile method that can be used. Okay. What we also know is that Falcon LLVM is a fully deterministic compiler. If we look at a method here, we can see that we can break that down into certain things. We can say we've got the initial intermediate representation, which is generated from the bytecodes and the live profile. We've got the queries and responses that are used to generate the optimizations for that method. And then we've got the machine code that's generated by the compiler. If we take identical input, meaning that we haven't changed the method itself, so the bytecodes are the same, and we've still got the same profiling data from our profile, that will generate the same set of queries and responses. And we know, because we're fully deterministic, that the output from LLVM will be identical. So there's no chance of it changing. We can use that fact to improve the efficiency of how things work. Looking at our diagram again, because we know that we have a fully deterministic compiler, in addition to recording the profile that I said earlier for ReadyNow, so those 4 pieces of information, what we can also do is take a copy of all the code that was compiled during the run of that application. put that into a file, and then we can use that as our compile stash. Effectively, it's a cache of the compiled code. That means that when we know we have the same set of inputs, rather than having to wait for the compiler to compile the code, we know we've already got a copy of that compiled code because it isn't going to change. So rather than compiling it, we simply draw it out of the cache and eliminate a whole lot of the work that has to happen there. When we look at that again in terms of our simplified graph, without compile stashing, we have this period of inactivity before the application gets going. With compile stashing, we can really squeeze that down and massively reduce it. In fact, we can reduce the compile time by up to 80%, and we can reduce the CPU load by up to 60%. What that means is we're now seeing an almost sort of perfect graph, not quite 100% perfect, but very close in terms of saying, right, what we've got is fast startup, because now we can start our application or our service in very much the same way as it was when it was running before. So we don't lose the effect of getting quick performance, but we also get all the advantages of just-in-time compilation, meaning we don't lose on the overall performance, which we would have done if we statically compiled that code. Statically compiled code gives us very fast startup, but it doesn't give us as fast overall performance. With this, what we're doing is getting that fast overall performance and the fast startup. Just to summarize then, basically faster startup or faster code or both. So microservices can benefit from fast startup. The ability to spin up services and react dynamically is all very good, but it's not the only performance consideration. Overall performance can be just as, if not more important. So if you've got longer running services, what you really want to make sure is that they can perform as well as possible to reduce the number of resources they require and therefore the cost in terms of your cloud bill. So you do have to think carefully about the different aspects of performance that we talked about at the beginning. So startup time, throughput, and latency. Which is the most important to you? Balancing those things based on what you need. But of course, if you look at Azul Platform Prime, that solves all of those problems. Eliminates latency associated with garbage collection, fast startup by giving you the ReadyNow profiles, and fast overall performance by giving you Falcon compiled code and all of that sort of stuff. So it's a solution to all of those problems. If you're interested in trying Azul's Platform Prime, you can do it for 30 days for free, and there's a web address here, so you can go to Products Prime Trial Download. And so with that, I'm going to say thank you very much, and we will now see if we have some questions.